Cool. Hello, everyone, to the fourth live lecture for Data 100 this summer. Our plan for today's lecture is a little ambitious. We plan on talking about these 5 ideas. We want to try and get through each of these things quickly just so we can touch on as many things as possible. So I will start off by talking about this higher level modeling recipe that you've heard in quite a few of the lectures. And I want to talk about how exactly that ties into scikit-learn. And I will also talk about root mean squared error and multiple R squared, because there are a couple questions about that on Piazza. And in the week 4 survey, quite a few students said they were unsure of why exactly RMSE couldn't increase on your training data by adding more features. So we will look at a concrete example of that. Then Alan will talk about one-hot encoding and go through some of the issues you saw in Lab 8 with singular matrices or nonsensical theta values and redundant features, which is something Joey briefly mentioned in the feature engineering lecture that came out on Wednesday. And lastly, if we have time, I will talk about what makes a model linear, because there were some misconceptions on the quick check question for, again, Wednesday's lecture. Before we get started, any logistical questions with what's going on in the class or how this is going to work or anything like that? Okay, let's get into it. So, you've heard me say, at least in 3 lectures, and I think it was in the Wednesday lecture too, that we have 3 steps in this modeling process. We choose our model, we choose our loss function, and then we determine the model parameters that minimize average loss across our data set. And so, the parameters that sort of minimize average loss, we call it optimal model parameters. And so when theta is wearing a hat, it means it's the version of theta that minimizes average loss across our data set for our choice of model and loss function. And so that on its own I won't talk too much about. But I wanted to talk about how the methods that we use in scikit-learn actually perform each of these steps. So in scikit-learn, which you've sort of been using in the labs this week, we would say something like model is equal to LM dot, let's get some space here. LM dot linear regression. Which of these 3 steps are we sort of at in the modeling process with just this one statement? It's kind of a vaguely worded question, but okay. So quite a few answers for the first step. So by saying model is LM.linear regression, we're choosing a model. And so you're right in that it encompasses the first step. But what you might not realize is that it also encompasses the second step. And to make that obvious, let's look at the scikit-learn documentation. If you look at the documentation, it says, if it's a linear model with coefficients, whatever, to minimize the residual sum of squares. That's another way of saying minimizing mean squared error. Just using slightly different terminology. You might remember that in lecture, we showed that mean squared error is the same as the average square of the residuals. And so this is exactly that. And so scikit-learn's linear regression is actually doing the first 2 steps for you. It's saying you're going to be using a linear model and squared loss is your loss function. Any questions with that? I don't want to say it was a trick question, but might not be what you were expecting. Okay, then we say something like model, there goes the keyboard again, model.fit xy. And that's sort of this 3rd step where we minimize average loss to determine the optimal model parameters. And so we know if we're looking at the linear model, or a linear model, I should say, the optimal theta vector for this model is x transpose x inverse x transpose y, where x is your design matrix and y is a vector of all of your true observed y values. In scikit-learn, how do we determine what these optimal model parameters are? Or I guess it determined it for us, but does anyone remember the syntax for determining, for printing out to us what the optimal theta values are? So a small detail. Does anyone remember? It's model dot something. So we fit a linear model. I want to see what the parameters are. Awesome, yeah. Coef and intercept, actually with an underscore after. So if I, fit my model and then look at model.coef underscore and model.intercept underscore, it will tell me what the optimal theta values were that it found. Any questions with that? Cool. And so there's another sort of stage in this process, but I don't want to explicitly list it as being one of these 3 steps. The last thing we tend to do is use our new model that we've fit to make predictions. That's sort of the context in which we're learning a lot of these tools in this class. So over here on the sort of math side, the way we make predictions now is we take a design matrix and multiply it by our optimal parameter vector theta, right? So we've found this optimal parameter vector from the previous step by minimizing average loss. We now know it and we can use it to make predictions. How do we make predictions in scikit-learn now that we fit our model? Maybe this is the right notation. How do we make these predictions? Great, dot predict. And so in scikit-learn, we'll say something like model.predict x. And that will give us, our model's predictions for what the y values should be for every x value that we pass in this predict function. And so thus far, we've largely talked about sort of fitting a model and then determining how accurate it was on the same data set that we use to fit the model. But in the sort of last part of the feature engineering lecture, we started talking about this idea of overfitting. When we add too many features and our model becomes too specific to the sort of noise in the data set that we've collected, and sort of the overarching goal of what we are doing with modeling is to build models that generalize well to unseen data, right? You've collected a bunch of, you've surveyed a bunch of people, you have their heights and weights, and now you have a great model that can predict someone's height given their weight. What we will practically use that for in this class is go and find a bunch of new people, get their weights, and, I guess that's not a great example because those are both things that you could observe. But you see my point. Like our goal with building models is to be able to make predictions for what we like when we don't actually know what the true y value is. And so in that, we will like to sort of test our model on data sets that we didn't use to create it. And we will look at an example of that shortly. But any questions with these sort of 4 steps and how they're related? Okay, let's take a look at an example notebook. So in this notebook, we are going to both use scikit-learn to, fit models and look at the predictions, but we're also going to look at root mean squared error and multiple R squared. So let's do it. And again, we will post this notebook after live lecture. So we're going to use the, tried and true Seaborn tips data set, which contains, a total bill column, a tip column, a sex column, and a bunch of others. We're going to focus mainly just on total bill and tip. And what we typically do is use total bill to try and predict what tip is. So I'm going to define a root mean squared error function, which sort of takes the mean of my true y's minus my predicted y's squared and averages them. So that's what this set of parentheses is doing, and then takes the square root of that. So it's the root, like the R corresponds to this part, the mean corresponds to this part, and the squared error corresponds to this part. Okay. So what I'm going to do is sort of create my linear regression model, fit it using total bill as my feature and tip as my sort of response. And I'm going to use that model to predict what these tips should be given my total bill data set. Okay. Why did I not include an intercept column? Right. If I just look at DF of total bill, it's just a single set of values. Great. Yeah, it does it automatically. Yeah, the default behavior of scikit-learn's linear regression, if you sort of take a look at it, fit intercept by default is true. So you don't have to worry about that. But anyway, so I've already sort of fit my model, and I can look at its coefficient and intercept. And in this case, there's only one coefficient. So this corresponds to the weight that is being multiplied by total bill in order to make our predictions. And the sort of y-intercept, or the constant term, is whatever this is. So I can look at the root mean squared of my model. It's 1.0178, which seems to be relatively small. And that kind of makes sense because these values are roughly linear. Okay, so that's our root mean squared error. What I want to do now is introduce a feature that is completely useless with regards to predicting tip from total bill. It's literally just selecting numbers at random and multiplying them by 342 because those are the 3 digits that my fingers happened to hit when I was making this notebook. Like, there's no significance to this whatsoever. So these values are generated purely randomly. And as a result, every time you run this notebook, the results are slightly different. So that might hurt us in a moment. But anyways, so what I'm doing now is fitting a new linear regression model using total bill and my useless column as features. And again, I'm trying to predict tip. And let's take a look at the RMSE of this. What do you all think this is going to be? Equal to the previous RMSE, lower than the previous RMSE, or higher? So the previous model just included total bill and an intercept term, and it was 1.0178-ish. What is this one going to be? We got a lower, we got a higher, another lower, at least equal, lower. Okay, let's find out. So it looks like 0.178500. It's getting intricate here. The RMSE of our previous model was slightly higher, right? So, you know, the first 5 digits or so are the same. You can see our first model, you know, after this point, there's a 402, whereas over here, it's a 046. So it is slightly, like ever so slightly lower than our first model. Why is that? We added a garbage feature, but why is the RMSE lower? Very slightly lower, but why is it lower? Any ideas? One answer is more degrees of freedom. It will ignore the garbage feature. It does not weigh the useless feature very highly. Yeah, you're on the right track. If we look at the coefficients, you can see the coefficient for total bill is 1.0503 or so, and before it was almost exactly the same. Sorry, is that the same? Yeah, sorry. This is multiplied by 10 to the negative 1. So the coefficient we found with our new model on total bill is roughly the same as our old model's coefficient for total bill. What's the coefficient for the useless feature? What is that? What is that? Yeah, it's tiny. It's something times 10 to the minus 6. So it's almost 0. So essentially, the reason our model didn't get worse here is because it assigns very little weight to the new feature. And the only reason there's any weight applied to this feature is because it must have allowed the model to attain a lower mean squared error. The way we were coming up with these coefficients was by minimizing mean squared error. And so if this feature didn't help us at all, the model could have just set its weight to be 0. And that's just effectively what it's done here. The reason it has a sort of non-zero weight that's really small is because this value must have helped lower mean squared error marginally. Okay, and we look at the scatter plot and it kind of looks like the same thing. Okay, let's take a look at multiple R squared. So we saw that the root mean squared error went down a little by adding a feature. Let's look at what happens to multiple R squared. So there were a couple ways that we sort of looked at the formula for multiple R squared. One was as being the correlation coefficient between our true y's and predicted y's squared. So, I mean, not that this really doesn't matter. It's symmetric. But so this is the correlation coefficient between our true y's and predicted y's. As we saw in lecture, if you use NumPy's correlation coefficient built-in method, it gives you a matrix of pairwise correlation. So we're indexing into that just so we get one number. So this is the correlation coefficient for those. And when we square it, that's how we define the multiple R squared value. Another equivalent formulation for models that have an intercept term is as the the ratio of the variances of our predicted y's to the variance of our true y. So that's this right here. So on the numerator, we have the variance of predicted y's. Denominator, we have the variance of true y's. And so, these are equivalent, but the second definition sort of tells us we can interpret multiple R squared as being the proportion of variance in our true y's that our predicted y's were able to capture. Is there a standardized RMSE value that helps quantify overfitting? So the thing with RMSE is that it could be anything. R squared must be between 0 and 1 because it's the square of a correlation coefficient or it's a proportion. RMSE could be like 10,000. It could be 4. It could be 0.01. So RMSE isn't on like isn't in like a interval in which we can look to see if there's overfitting or not. The way we look at overfitting is by comparing our model's training error to its testing error, which is what we are about to do momentarily, but that will be the focus of Monday's lecture. And so essentially what we do is we set aside some of our values our data set that we have to us and don't fit our model on those values, but instead we just use those values for evaluating how good our model was. And so if our testing error is significantly higher than our training error, then it indicates that we were overfitting to our training error. But we will get there. One method that you should be aware of is that scikit-learn has a built-in .score method that computes the multiple R squared value for linear regression models. And so you can see here, it gives us the exact same number roughly to numerical precision. One thing you should be aware of. Model.score works differently for linear regression models and logistic regression models. So we haven't talked about logistic regression yet. It's going to appear in lecture on Wednesday and Thursday. When we do that, model.score will tell us the accuracy of our model. So the number of times we made a prediction that was exactly correct. When we are dealing with regression, our goal isn't directly to make as many predictions exactly correct as possible. Instead, it's to minimize the sort of average of the squared losses. And so model.score works differently for linear regression than it does for logistic regression. But my point in bringing this up is that you should not interpret this number as being the accuracy of your linear regression model, because accuracy for linear regression isn't defined the way it is for a classification model. So that might not make that much sense right now, but you can come back to this sort of in a week when you're studying for midterm 2, and that will prepare you for any trick questions that we might ask. So you're welcome. Now let's take a look at the multiple R squared value for when we added the useless feature. You can see that, again, it went up, but barely, but it went up. So you can see the first 6 or so digits are the same, 4, 5, 6, 616. But after that, there's a 9 for the second one, and here there's a 5. Oops. So the multiple R squared value did go up, but barely. Why did it go up? Why is this multiple R squared value higher than the other one? Any ideas? we interpret multiple r squared as being the proportion of variance in our true y values that our fitted values were able to capture. And again, fitted values is another term for predicted y's. Is it the case that this new useless feature we added is able to explain or help explain more of the variation in y than sort of total bill was able to do on its own? Is that the case? Probably not, right? We just added a bunch of random numbers essentially. But since we were able to make slightly better predictions with this sort of new fitted model, the r squared value went up. But my point in showing you this is that a higher r squared value doesn't necessarily mean your model is actually better, because no one, practically speaking, would use this useless sort of feature because it doesn't add any predictive value. And so let's wrap up by looking at how this model performs on unseen data. So what we're going to do is separate our data into training and test. And this was sort of done a little at the end of Wednesday's lecture and will be the focus of Monday's lecture. But we're going to set aside some values to only be used for seeing how well our model performs. And so we will train our model on 3/4 of the data that we have available to us and use the remaining quarter for just seeing how well it worked. So don't worry too much about what's going on here. This will be the focus of the lab that you have on Monday. But essentially what I'm doing is I'm taking all of the indexes in my data frame, shuffling them up, and I'm going to take the first 3/4 of them and say those are the indices corresponding to my training data. And I'll take the last quarter. Visually, that was probably like 2/3 and 1/3, but it's fine. I'll take the last quarter and say that that's my testing data, okay? The reason we're shuffling it is because we want to get rid of any potential unseen biases that there may be due to the pre-existing ordering of how our of our data set. Okay, so split point is just going to be the point that's 3/4 of the way through my data. More typically, you usually use like 80-20 as your like proportion. So this would be 4/5. But just for illustration, we'll do this. And so now train contains 183 rows, and you can see this index isn't in order because we just took a bunch of random ones. And test contains 61 rows, and if you add those up, we get 244, which is the total size of our data set. So what I'm going to do now is fit our model just using training data. So before we had DF of total bill and DF of tip, meaning we were fitting our model on all of our values. Now we're just fitting it on those 3/4 that go in the train data. Then I'm going to predict two sets of Y predicted values, two sets of fitted values. New pred1 train is my predicted Y values for my training data. Okay, and so the thing that I'm passing into model.predict is my training values for total bill. The last line is predicting what the Y values should be for my testing data. Up until this point, at no point has my model seen what the Y values for the testing data is. So our model's never seen this column, but we're still going to try and predict what its values should be. Okay, and so now that I've done that, what I'm going to do is compute the root mean squared error for my model on both my training data and my testing data. Okay, so this first line, I'm saying, give me the root mean squared error between my training Y values and my predicted training Y values. The second line is saying, give me the root mean squared error between my test Y values and my predicted test Y values. And we look at the root mean squared errors. In this case, it happens to be true that our training error is greater than our testing error. Why did this happen? This isn't really the point of this exploration, but why did this happen? Is like, did we break something? Or is this legal? We didn't get lucky. It's just telling us that our model wasn't overfitting to our training data. But let's take a look at what happens when we add this useless feature. So we're adding this useless feature. So now the effects are not going to be as dramatic as they could be because the weights will be set to 0. But what I want to show you is that root mean squared error can increase if we're looking at testing root mean squared error. And so you can see the training RMSEs still went down between the two models. So we have 0.0596 versus 0.595. So the training RMSEs decreased. The testing RMSE increased though, right? So the RMSE on our testing data went from 0.8902 to being 0.8906. So when we're looking at testing data, adding more features can make your model worse. And that's why you need to be cognizant of what features you're adding, and you have to make sure that you're only adding useful features. Okay, and yeah. So you can see the coefficients for the total bill column are roughly the same. And again, the coefficient for the useless column is close to 0. Yeah, so this is directly related to the bias variance trade-off, but those connections will be made a little more clear in Monday's lecture. How does RMSE change with the validation set? So the point of a validation set is to sort of mimic our testing data. So how this pipeline sort of works is that you only use your testing data at the very end when you're done with your model and you're ready to sort of, send it off to for someone to use in production. Your validation data is sort of like it's like a proxy for your testing data. It's like a testing data that you can reuse, but you also want to make sure that you're not overfitting to your validation data, which is why we have something called cross-validation, which again will be the topic of Monday's lecture. So my point in showing this exploration isn't to sort of go over all of the nuances of validation and cross-validation, but it's to sort of get you thinking about these ideas. Is there a formal proof that more features can only decrease root mean squared error? To be clear, that is only true when we are looking only at the data that we use to train our model. And the proof is that if that new feature doesn't help our model's predictions, its coefficient will be set to 0. Because the goal is to minimize mean squared error. And if new features don't help minimize it, their weights are set to 0. But of course, it's not true when we start looking at testing RMSE, because as we saw here, it increased by adding this feature. Okay, I'll stop this sort of section here because we still have quite a bit to get through. So I'll pass it off to Alan. And yeah. It's enabled.
Yeah, one other way to look at it is that you can always do as good as your original model by setting the weights to 0 for the new features. So you'll always do as good. You can't do worse. Let's see. Lost my notebook. All right.
But yeah, again, the whole point is, while you can't do worse on your training data, on your testing data, you can do worse. And so you don't want to just start adding features haphazardly. Like you need to haphazardly is probably the correct pronunciation. But you need to be careful and make sure the features you're adding are actually useful.
Okay, so this is a separate notebook, but we'll combine my notebook with Serge's and post that after this. So this is the same tips data. I'm gonna skip some of this for now and come back to it. But let's say we just use total bill and sex as our feature matrix without an intercept term. So what would be the rank of this feature matrix? So recall that the rank is the same as the number of linearly independent columns. We're not going to go into detail on what like rank is exactly, but okay, I'm seeing a lot of 2s. Anyone want to explain why they think it's 2? Like, where's the linear dependence coming in here? Two sex columns are linearly dependent. But is there a way to create one of the columns using the other columns, a linear combination of the other columns for this example? Total bill is- Don't have a column of one. Yeah, exactly. So that's kind of the trick with this example. The rank is actually 3 because although these two features are redundant, like redundant as in like if you know it's female, like obviously then I mean you know whether it's female or not. You don't need to like also know whether they're male or not. Like if female is 1, then you know male is 0. If female is 0, you know male is 1. But the trick here is that as was mentioned, we don't have a column of 1, so there's actually no like linear dependence here because I can't construct this column using this column. There's no way I can't like take a multiple of this column and make this column. But okay, let's say we have a column of 1s now. So in that case, the rank is still 3 because I can construct the male column using the intercept column subtracted, or using the intercept column minus the sex female column will give me the sex male column. So although there are 4 like columns here, one of these like 3 columns is redundant because I can make the sex female column using the sex male and intercept columns. But here there was no intercept column, so there was no linear dependence relation in this example.
Can you do the like series? Like, can you show exactly that intercept minus sex female equals sex male?
Yeah, let's see. Live coding is hard, but hopefully I can do this. So, let's see. Okay, yeah, so I can take the intercept column, subtract it from the female column, get the first 5 rows, and this is the exact same as this male column. Likewise, if I do this, if I take the intercept and subtract it from the male, I get the female column. Will we typically have an intercept in our DF, or we have to add it to sklearn automatically? So, as Serge mentioned earlier, linear regression, the linear regression, like the object for sklearn, automatically adds an intercept column by default. So you don't need to add it to your data frame, but you can set the fit intercept parameter to false if you don't want it to automatically add an intercept column, which I'll actually use that later in this notebook. Okay. Any questions on these 2 vanilla examples before move on? All right. So hold on, x5. So we can also, as another example, one-hot encode the sex column and the smoker column. So what is the rank if I do one-hot encode both of them but don't include an intercept term? So there are 5 columns here. Five. Okay, so the answer here is actually 4. The reason being, I can construct the difference here, like between this example and this example, is that I can construct the smoker yes column by adding the sex male column and the sex female column and subtracting the smoker no column. So let me make that clear. I can add X5 sex male plus X5 sex female. So this by itself will give me a column all ones because you're either male or female, and if you add these two, you basically get the intercept term. But here there's no intercept term. I'm just saying that you get a column all ones. And then if I subtract that from the smoker yes column, okay, this is, oh, right, I took the last 5 rows. -5, yeah, okay. So getting the last 5 rows of this, I get the smoker no column, 1, 0, 0, 1, 1. So I can take male, add it to female, and subtract it from yes. So one of these like 4 columns is redundant essentially here. So yeah, this is like different from the first example I went through, because there was like this extra, you're one hot encoding 2 features instead of 1 feature. And then I can also add an intercept column, but the intercept column is redundant with like these 4 features still. So the rank is still 4 because I can construct the intercept column by adding the smoker yes and the smoker no column, or by adding the sex male and the sex female column. So the intercept term doesn't like add any information here. Okay, so this is just in terms of rank. So why is rank important? Like why is rank important? Does anyone want to answer that? Why do we want the rank to be the number of columns instead of like less than the number of columns? Need to invert in least squares. Yeah, exactly. So the rank of X, or like the rank of our data matrix that we're using, is the same as the rank of X transpose X, which is the term that you need to invert for least squares. And so if this does not have full column rank, if the rank of the matrix is not the same as the number of columns, then you won't be able to invert your X transpose X when you're solving the normal equations, which means you won't have a unique solution. So I'm going to go back to this more complicated example. So why do we need one hot encoding in the first place? So I can try like just doing a linear regression on the everything but the tips, and try to predict the tip from that. But they'll like yell at me and say, oh, I can't because I can't convert a string to a float because it's trying to like find a data matrix, but here there's like strings. So in order to encode the sex column or any of these like categorical variables, I need to one hot encode them so like you can use it as a part of your data matrix. So back here I used pd.getDummies. So that's one way you can do one hot encoding. Back here I use pd.getDummies. That's one way you can do one hot encoding. Another way you can do it is this thing called dict vectorizer in scikit-learn. Because we don't have that much time, I'm not going to go over the syntax here, but essentially does the same thing. It's a little bit more nuanced, but it does like the same thing. So here's the data matrix with like all the features one hot encoded, including an intercept term. There's 13 columns here, but the rank here is only 9 because again I have like the redundant features of like female and male and smoker, no, and yes. So the one way to address that is I can drop the first column of each of our one hot encoded features, or here's just some random column, doesn't matter really which one you drop. The idea is that if I drop the male column, or if I drop the female column, the male column already has all the information I need. So I don't need the female column. And likewise, I don't need like the smoker no column or like the time dinner column. because like if I know that it's lunch, then I know it's not dinner, and vice versa.
One thing I'll point out is that this, what Alan just said, is a question on the homework that's coming out on Sunday. And last semester, many students got it wrong. They, like, for example, let's suppose the three categories were low, medium, and high. The question is, why do we not need, like, why do we remove the medium column? And a lot of students put, well, because medium doesn't tell us anything. And the actual reason is because you need to remove one of the columns to get rid of this redundancy. So now you know.
Yeah. So yeah, if I remove those, hold on, I think I ran that twice. Run these. Okay, and then if I remove them and look at the rank, now it's full rank. So there's a unique solution to least squares now, so there's no issue with invertibility. Okay, this is just another way to do it with pandas. I'm not gonna go through it. But one thing to note is that there's this drop first parameter for pd.getDummies, and they'll automatically drop the first of the one hot encoded columns. So like you don't have to do that manually as I did here. Okay, let's get on with duplicate features. Okay, so suppose I have a model with just total bill and size, but I include the size feature twice, and I have an intercept term as usual. So what would be the rank of this matrix? There are 4 columns here, but the size appears twice. Three. Yeah, so it's 3 because the size is redundant with the size. So only like three of the columns are not redundant. And again, the issue is that like if it's not full column rank, then you can't invert x transpose x and find a unique solution to these squares. Okay, so one thing we can do is I can fit because linear regression, like the scikit-learn linear regression is like flexible for like these situations, I can still fit a model and like find some coefficients. It'll just like somehow optimize it behind the scenes. I think you saw in lab 8 that you could still like run SciPy optimize even if the data matrix was not full column rank. It'll just like find one of the optimum points, even though there's not necessarily a unique optimum.
And the lecture on Tuesday, gradient descent, will show you one of the many ways that you can like numerically arrive at a solution, even if there are multiple.
Okay, yeah. So looking at the coefficients, and then I can use like model.predict as like Serge showed to find like the first 5 predictions for our data set. Another way to do this is I can take the first 5 rows of my data and take the dot product of that and your coefficients. So that's like the x theta thing that Serge was showing, except here I'm just taking the first 5 rows. So that gives me the same output as this. And another thing I forgot to mention is that here I'm using fit intercept equals false because I already included an intercept term. So I don't want scikit-learn to also include an intercept term. And if you like try to look at the coefficient of the intercept, like it'll just give you 0 because it didn't have an intercept term. So one question is, okay, our model is like theta 0 plus theta 1 times size plus theta 2 times size plus 33 times total bill. Because we have size twice, there's a way to change our model coefficients so that the predictions are the same. So like this, you can change the model coefficients so that this outputs the same thing, regardless of like what the size or total bill is. So can anyone think of a way we can modify the coefficients so that this like equation, this model stays the same and like all the predictions are the same, regardless of what like the size and the total bill is. Okay, for the sake of time, I'm just gonna go over this. So one thing you can do is I can subtract 100 from the theta 1 parameter and add 100 to the theta 2 parameter. And those coefficients will result in the same predictions as before. So model, let's see, let me output. So these coefficients and these coefficients are the same, except I added 100 to this coefficient, or subtracted 100 from this coefficient and added 100 to this coefficient. And that resulted in the same predictions as before. Convex combination of, yeah, basically. So the thing is, I could like add whatever number I want. I can add like this big number here. And this is like a huge, this is a really small number, this is a huge number. It'll still give me the same predictions. So that's why you saw in lab 8, like your coefficients completely blew up if there was redundant features in your design matrix. And like you could get like weights that are this big because I can just like subtract anything from one weight and add anything to the other weight. And here's like a proof of that. Like if I take theta 1 minus 100 and theta 2 plus 100, and I work out the math here, I subtract 100 times size and add 100 times size. So those cancel out regardless of what this number is. So this could be like this big number here. It'll be the same thing. And this results in the same model as before. Any questions on this section? Like, okay, I'm gonna rush through this. Yeah, our models with blown up coefficients work just as well because the predictions are the same, and we found from like the LM.linear regression automatically minimizes the residual sum of squares, as Serge mentioned. And if the predictions are the same, then the residual sum of squares would also be the same. So the model is basically the same, and like it works just as well, regardless of what our coefficients are, as long as like I do this consistently. So I can also add 2 times size as a feature. The rank would still be 3 because I can just take this column, multiply by 2, and get this. Likewise, I can do the same thing, and I'll see that I can't just subtract 100 and add 100 because I have 2 times size now. So I have to do subtracting 100 and adding 50 instead. So you can play around with the math with that, but it's essentially because I have 2 times size. I need this weight that I'm adding here to be half the size of this weight. And that'll give me the same predictions as before. Another thing I can do is add 2 times size plus 3. So because I have an intercept term, the matrix rank here is still the same because I can add 2 times this column and add 3 times the intercept column to get this column. So there's still one redundant feature here. So they'll run into the same issues as before, where like here my rank was 3 and here my rank was also 3. And then I can add size squared. So instead of 2 times size or 2 times size plus 3, I can add size squared as a feature as well. So what do you think this would output if I add size squared as a feature? Would it be 3? Would it be 4? Would it be 1, 2? Yeah, so it's 4 because now there's no linear relationship between size squared, and intercept. Because you're taking the square, there's no longer a linear relationship. Now it's like a quadratic relationship. And what rank looks at is linear relationships and linear dependence. So because there's no linear relationships anymore. The rank is 4, and now I can do least squares and everything and get a unique solution. All right. Any last questions, or I'm gonna pass it to Serge?
Cool. We don't have a ton of time, but in hopefully 5 minutes or so, I will try to get through as much of this as possible. So I want to talk about what makes a model linear. Is this a linear model? Let's start with that question. So here, pretend X corresponds to a single row of our design matrix. So pretend our design matrix for now just looks like X1, X2, or sorry, first row and then column. So X21, X22, so on and so forth, Xn1, Xn2. And so the X here corresponds to a single row from here. Is this a linear model? Let's see what the chat says. We're getting some yeses. Can someone tell me why this is a linear model? You're right, but why? Great, yeah. It's a linear combination of our features, or it's linear in terms of our parameters. I can write this as being sort of like f theta x. I can write this as being the dot product between my x vector and theta vector, where x is this vector of 1, x1, x2. Scroll down a little. Let's bring this over here maybe. Sine of x1 and cos of x1, x2, e to the x1. This is my x vector. This is a row of my new design matrix. And then theta is just, this vector of theta naught, theta 1, theta 2, theta 3, and theta 4. And so if I take this dot product of x and theta, the result is this. So anything I can write in this form gives me a linear model. Sure. So is this model linear? Well, I mean, it's not going to be linear by the positioning of it, but let's look at it anyways. Theta naught plus theta 1 x plus theta 2 sine theta 3x. Is this linear? It's not, because we can't write this in the form x transpose theta. If we tried to, this x vector will end up with the theta in it. But our features and their parameters need to be separate. Right? So there's no way to sort of write a design matrix or separate this into an x vector and a theta vector who we could dot product to get this result. And it's because the theta 3 is non-linear here. If the theta 3 wasn't there, this is linear. The way this is written, it is linear. The theta 3 being inside the sine makes it non-linear. Is that clear? So the features themselves don't have to be linear. The features themselves could be anything. Which is why, sort of when Alan was going through the demonstration of adding x squared as a feature, we were still doing linear regression. Because you can put whatever you want in your design matrix, as long as your model is linear in terms of the parameters. Put here. So your question is, can a non-linear model be written so that it is, or is that a limitation of linear models? That's a good question. So here the non-linearity comes from the fact that, again, theta 3 is being, like the sine of theta 3 is being taken. And so there's no way to express this as a linear model. Yeah. So I guess that is a limitation of linear models. But you can really model anything with a linear model as long as the parameter itself remains linear. So like this specific thing you couldn't do, or you couldn't have like, let's say, like e to the theta 3x, for instance.
So
But
one
yeah.
thing you can do if you want the sine theta 3 of x, if you have like some insider knowledge of like what theta 3 could be, you can just add more parameters to your model. So like you could add theta 2 sine x, theta 2 sine 2x, sine 3x, and so on. Or not theta 2, but like theta 3 sine x. Okay, theta 2 sine x plus theta 3 sine 2x plus theta 4 sine 3x, and just like add more features that like have a different, I think this changes like the amplitude of the sine, but like have different basically amplitudes.
Or yeah, you can just treat some constant times x. You can just test a bunch of different features individually using cross-validation and see which one is a sort of better choice. So it's not that you're unable to optimize that nonlinear parameter. I'm glad you asked that question. It is still possible to determine the optimal thetas here. It's just not a linear model. And actually, in homework 7, which will come out next Thursday, there is almost this exact question. It's very similar. And you manually sort of implement gradient descent so that it optimizes the set of parameters. So it is not the case that you can't optimize it. It's just not a linear model. And so you can't sort of say your model is x times some theta vector. But it's still a model. You can still use it for things. It's just not linear.
Yeah. So you can't use like the normal equations to like, solve for the optimal parameters.
Yeah. Nor can you use like scikit-learn's linear regression. But it's still a model. Still a model. Just not linear. Glad you asked that question. Okay, any other questions before we call it a day?